Good day, Doctor. We are Group 7 and we would like to present on our second phase assignment. The objective is to remove the noise from audio file that we are given. So here's our oral step. First thing first, we need to find out our time domain and frequency domain input signals, and then we design our filters. After that, we check the stability with Z transform. And lastly, we find out the output signal based on convolutions. Here's the first step, which is sampling. Based on the code, we need to do the audio read function first. So we will get the data samples in X and then also the frequency in Fs. And then we set our correct array of time using these two lines of code. And then finally, we plot the discrete time domain plot using the stem function. Using the code above, we can visualize the audio signal in time domain. But there's a catch. We can see that the noise is not clearly visible.
Hi, I'm Emily. To clearly visualize the noise signal, we need to use discrete time Fourier transform DTFT to convert the discrete time signal from time domain to frequency domain. The DTFT of the audio signal was computed by using this formula: x equals to xn exponent negative omega n from 0 to number of sample minus 1. And the spectrum was evaluated over the range from 0 to pi to obtain the half spectrum. And the angular frequency was converted from radian omega to frequency in hertz by using the sampling frequency Fs. Then the magnitude spectrum was then plotted to identify the noise frequency components present in the signal. From this DTFT magnitude spectrum, we can clearly see that there's a clear noise spike was observed at approximately 800 Hz. So this noise will be later then filtered out using FIR and IIR filter design.
Hello everyone. So now I will explain about the windowing method. So first of all, let's just begin with the equation. So this is the general equation for the windowing method, and this one is the specific ideal bandstop response because our group is trying to design a bandstop filter in our assignment. And the WN is actually the window function. And as you can see, our group is trying to use 3 different windowing methods, which are Hamming, Henning, and Blackman, to design the FIR filter. And these are the MATLAB code that we use. So these are the functions that we use for 3 different windowing methods. So these are the output results for our FIR filter by using 3 different windowing methods. So as we can see, the impulse response for 3 windowing methods are almost same, but their performance in frequency domain are different. So based on their performance, we are selecting Hamming window because it offers an optimal balance between transition width and able to achieve the maximum possible noise attenuation.
For the bilinear transformation, which is an important step in designing the IR Butterworth bandstop filter. It converts the analog filter into a digital filter so that it can be implemented in a digital signal processing system. The transformation is represented by this equation. This equation maps the analog S-plane to a digital Z-plane while preserving the stability of the filter. Next, for the MATLAB implementation, although the bilinear transformation is not explicitly written in the code, the MATLAB performs it internally when executing the Butter function. This expression describes the relationship between the analog frequency and the digital frequency, known as frequency pre-routing. MATLAB automatically performs frequency pre-routing together with the binary transformation to ensure that the desired stop band frequency we set are accurately preserved in the final digital filter. This is the output result B and A coefficient from 0 to 12. This coefficient form the digital transfer function Z, are then used by MATLAB filter function to remove the unwanted noise that we set before. In summary, the analog Butterworth filter will convert into a digital filter.
Good day everyone, now I would like to explain the Z transform analysis of the FIR and IR filters used in this assignment. The Z transform converts a discrete time signal into the complex Z domain and is used to analyze the filter's poles, zeros, stability, and region of convergence, or RC. Here's the MATLAB code used to generate the pole zero plots. As shown in the figure, the FIR filters has all 250 poles at the origin, and its ROC is the entire Z-plane except Z equals to 0. Since the ROC includes the unit circle, the filter is stable. However, it requires a high filter order of 250 to produce a sharp stop band between 750 and 850 Hz. For the IR filter, all 6 poles lie inside the unit circle, and its ROC is outside the outermost pole. Since the ROC also includes the unit circle, the filter is stable. The poles and zeros near the unit circle allows the filter to achieve the same bandstop response with a much lower order of only 6.
After checking the stability of the filter design by using Z transform, we will then need to apply the filter design to the input audio signal in order to produce the filter output signal by using convolution. And this is the MATLAB implementation. FIR filter signal was produced by convolving the audio signal X and with the FIR impulse response H. Then we will need to plot the DFT spectrum original signal versus filter audio signal to observe the filtering effect in the frequency domain. By observing this DTFT magnitude spectrum, the unwanted noise components around 800 Hz is reduced after FIR filtering, showing that the bandstop filter is effective in attenuating the noise within the selected stop band. For RIR filter, we need to use filter function instead of using convolve because RIR filter is defined by both numerator coefficient B and denominator coefficient A. Therefore, IR output is obtained by using MATLAB filter BAX function, which implement the difference equation of the IR filter. And by observing this magnitude spectrum, unwanted noise component around 800 Hz is reduced after IR filtering, showing that the Butterworth band stop filter is effective in attenuating the noise within the selected stop band.
This concludes our presentation on audio signal filtering analysis using MATLAB. Thank you.